Hello and welcome to Spaced Out. I'm Sarah Begum, your host, and today I'm really excited to introduce MEENAKSHI WADHWA. So MEENAKSHI is a planetary scientist and educator who studies the formation and evolution of the solar system through the analysis of planetary materials including meteorites, moon rocks, and other extraterrestrial samples sent from spacecraft missions. She is the director of the School of Earth and Space Exploration at Arizona State University. She is also a research associate at Field Museum of Natural History in Chicago, and she's won numerous awards. If I label all of them, I'd be here forever. Basically, she's just amazing. Hi, MEENAKSHI. I've really been looking forward to this interview, as I've said before, so welcome to the show.
Oh, thank you so much, Sarah. I'm really pleased to be here.
It's a bit of a big question. I understand that from one of your TED Talks, the messengers from faraway worlds. I really love that, by the way. It's really insightful. really great teaser for this. That the age of our solar system is 4.5679 plus 0.0003 billion years old. I had to look at my notes for that. Based on your studies so far, can you explain how the solar system formed and evolved over time?
That could be an hour long or a few hours long.
I could be here for hours listening to you.
No, in very sort of summarized form here, our solar system actually came about from a cloud of gas and dust, a region of our inner kind of interstellar space. There's basically molecular clouds, which are a little bit denser in terms of the amount of gas and dust that there is. And then there's regions there that sometimes, and we don't fully understand exactly the processes that cause that to happen, but there's denser regions that then collapse to form young stars. And our sun likely formed in a region like that. It was probably formed actually from, studying meteorites again. We understand that it probably formed in an area of our galaxy that actually was quite different 4.5 billion years ago than it is today. Formed in a really sort of, probably a very active star forming region, actually. And so there were young stars forming in our neighborhood, probably. There were supernovae potentially going off nearby as well. So it was probably a much more active, dynamic, violent place than what we see around us today. But yeah, so the collapse of that cloud of gas and dust really was the process that started our solar system. And then as it sort of started to form, it basically, because of laws of physics and conservation of angular momentum, as it basically became a disk with a central star. And then finally, as things sort of started to cool down, you had condensation of the first solids, which then accreted to form solid bodies, first meter-sized, and then they grew to kilometer-sized, and then planetary scale bodies. And so there was, and that happened really relatively quickly, actually. Within the first 10 million years of solar system history, actually was probably one of the really most active phases, when rocky bodies and gas giants were all starting to form, and then obviously ultimately we formed the kind of solar system architecture that we see today. But there's a lot that's happened in between, that first collapse of that cloud of gas and dust and where we are today. There's we understand a lot about that actually from studying meteorites.
How were you able to, carbon date or measure the age of these meteorites and these samples? Because this, when you say figures such as billions of years ago, how do you know how old these samples are?
Yeah, so there are actually some clocks that we can use, and those clocks are actually used in geology and terrestrial sciences. They have been for a long time, but there are some isotope systems that we use, particularly some radioactive elements like uranium, for example. By using those kinds of clocks, and actually you mentioned, carbon-14, that's actually something that's used for more recent things that happened in Earth history. We can't actually carbon date any materials, actually. Maybe, anything older than about 20,000 years or something like that would be kind of hard to date with that kind of methodology. But actually, the kinds of clocks that we use involve elements like uranium, like I said, and that have longer half-lives. And so we can actually date very, very precisely how old some of these first solids that formed in our solar system are. And these, of course, we can find these in meteorites. And that's part of what we do in my laboratory, actually, is to sort of date these materials using clocks like the uranium-lead system, for example, where the uranium isotopes decay to lead isotopes. And then there's other systems as well that are appropriate sort of chronometers for dating these types of materials. And so we use those, and some of them actually give us very, very precise, relative timescales of when these things were forming. And so we actually, know a whole lot about what was happening just from sort of studying these rocks that we have.
You're like a space archaeologist.
Yeah. I like to say we're sort of like cosmic, detective CSI, type of analyses.
I love it. I love it. I'm just, I'm just in my seat. I feel like I'm watching a really cool Nat Geo documentary. Listening to you speak.
It is kind of fun. I mean, I love, just that kind of, the nature of the work is like detective work. You're putting together clues to kind of, figure out who done it, it's
figure
fun.
out how many billions of years it is.
Yeah, exactly.
And where it came from.
Exactly.
So what is the earliest sample you've come across in your work so far? Where did it come from, and how were you able to measure that?
Yeah, so there are actually some specific objects that we find in certain types of meteorites. And these solids actually were, we think, the very first materials to condense from the cloud of gas and dust that was our solar system initially. So the solar, we basically call it a solar nebula at that early phase when it was still mostly all gas and dust. And as things were starting to cool down in the midplane of that disk, you had the very first solids start to condense. And they formed these little grains, some of them maybe as large as maybe a centimeter across. Those are the largest solids that we find of that nature in meteorites. Most of them were actually much smaller, millimeter-sized grains. So these condensed out in meteorites. And so we can actually, at the current time, look at certain classes of meteorites that are among the most primitive types of materials. They're called chondrites. And we can pull them apart, and we can actually pick out those earliest solid grains because their chemistry is quite different from a lot of other materials. So we can recognize them by actually looking at them and looking at their chemistry. And we can then subject them to the cruel and unusual things that we do in my laboratory, where we separate out the radioactive material, the radioactive isotopes from the daughter isotopes, and we can then date them very, very precisely, actually.
Was there a specific one that you came across that you can tell us about?
Yeah, so
the earliest?
Right. So the age of the solar system that you just talked about earlier, we know that from actually dating one of these types of solids. So that's the oldest solid that we've ever measured in our laboratories. All these kinds of tiny grains. They're very refractory grains, meaning that they condense from elements that condense at very high temperatures, basically. And so we've dated some of those materials, and the date is, 4, 5, 6, 7, 9, as you mentioned, 4.9 billion years. And that's the oldest sort of, solid objects that we know about and that we've dated in laboratories.
I've got that name, that number etched in my mind, 0.0003.
Yeah.
I just had to look at it for a good few minutes. Like, really? Wow.
Yeah.
So, what did you learn from studying moon rocks? Because that's another sample that you've studied. And which mission did it come from?
So, in my career so far, I've looked at a few different moon rocks. I mean, the Apollo samples that were brought back in the late 60s, early 70s, we have something like 800 pounds or so, which is about approximately, I guess 300 something, almost close to 400 kilograms of material. And so there's a lot of moon rocks available for study. And, and I've studied a few different ones for different types of investigations.
You have to tell me what these investigations were.
Yeah, so early on it was mainly, I was interested in studying the chemistry, the trace element chemistry, and using them again, just like a detective would, try to piece together how these rocks actually formed on the moon, the history of sort of melting and solidification that they went through. So I studied basically their chemistry to try to understand that. And more recently, actually, my current project studying moon rocks is actually looking at, water in moon samples. And so we were just funded by NASA, actually starting of this year. And we are studying volatiles, including things like water in these moon rocks, to try to understand the history of water in the moon. Because one of the really strange things that's happened over the last couple of decades, and this is just very recent, and it shows the power of actually bringing back samples from other places in our solar system, is that, these moon rocks were brought back in the late 60s. It's been almost, it's been over 50 years, right? I mean, we have some of these samples now for decades in our collections. But when they were first brought back, the technology just didn't exist to actually measure the low amounts of certain types of components in these rocks. Mm-hmm. And now actually we can do that. And so, many decades later, we're starting to study these moon rocks again with the newest analytical capabilities that we have now. And we can actually very, very precisely measure, how much water there was. Our techniques are able to actually detect much lower abundances of things that we couldn't even dream of measuring them, a few decades ago.
Are you allowed to tell us about the water retention in these samples and what you learned about water on the moon from these samples? Because from my recent interview about the moon village and about the lunar surface exploration, I was told that there was water on the south pole of the moon, and there are various missions from different nations to retrieve those samples or even mine this. So I'm interested to know from your perspective what you understand about water on the moon.
Yeah, so you're talking about the polar, the permanently shadowed polar regions of the moon, where they think there might be some water reservoirs near the surface, actually.
Yeah,
and that's a really interesting question, because we don't really understand whether that, we think most of that water actually might have been delivered by cometary materials or things that were actually water rich that actually delivered that water to the surface of the moon sometime later in its formation history. And because the permanently shadowed regions are so cold, they act like cold traps. And so any bodies bringing in water and molecules of water that are sort of bouncing around on the surface, if they get trapped in those permanently shadowed regions, they can never escape out. And so we think that's how much of that water was built up. What I'm really very interested in, though, is the water that's in the interior of the moon. Something that tells us about the original formation history of the moon, the process by which the moon formed, and how is it able to actually retain that water, considering what we know about the history of the moon. The most common sort of commonly believed hypothesis at the current time, based on a lot of analyses that have been done, is that the moon actually was formed in a giant impact very soon after the Earth was almost fully formed. So we're talking about, close to 4.5 billion years ago now, right? So way back in the past, we believe that there was maybe a Mars-sized object, and actually there's a name for it as well. It's called Theia, and that object slammed into the early Earth, and it created all this, debris from which basically the moon assembled from that debris disk. And so in that kind of violent process, how do you actually retain things like water in the interior of the moon? And so there's a lot that we can learn about the history of the formation of the moon and early processes in the solar system just from studying these moon rocks and trying to understand the history of water, not just on the sort of superficial aspects of things, but in the interior, because the rocks that we're studying are actually rocks that formed from cooling of magma that was produced in the interior of the moon by melting in the deep interior of the moon. And so I'm interested in that component of water, and that's really interesting.
So interesting. I never really thought about this until you just mentioned it to me, water inside the moon.
Yeah, so I mean, it's, that's what
who would have thought of that? It's just because first of all, I didn't even know there was water on the moon, and then I learned there's water on the moon. But I'm thinking about the surface of the moon, because when you think of South Pole of the moon, you immediately just think South Pole of the moon. You don't think inside the moon. So it would be interesting to know what the chemical makeup of the moon is, and you may be able to figure this out from the samples that you study, which brings me to my next question, because you study asteroids, moon rocks, and other extraterrestrial samples, but what are the chemical makeup of these samples you find? Are they similar, or are they wildly different?
So I mean, in broad terms, the kinds of rocks that we find on the moon are, many of them are actually very similar to what we call basaltic rocks here on the Earth. There are some differences in their chemical makeup. Some of them, for example, have a lot more titanium, the element titanium, than others. And there's some somewhat different compositions that they carry that tell us something about the history that they went through on the moon itself. And so and tell us basically the composition of the interior of the moon is what we can learn from looking at their detailed chemistry. But in very sort of broad brush terms, they're actually very sort of similar. I don't know if you ever had the chance to see a moon rock.
No, not yet.
That's not. Oh, I sure hope you get a chance to do that. But the moon, when you look at it, you see, there's the man in the moon, that where you've got the dark regions and you've got the lighter regions. And the dark portions are actually very similar to, basalts here on the Earth. The lighter regions are actually also, made up of mainly a mineral called anorthite. And there are similar rock types that we can find on the Earth as well. But of course, on the moon, there's these huge regions, particularly on the far side of the moon, that are mainly anorthite. And we think that's part of the primordial crust of the moon after it was just, we think it started out as almost completely molten and then started to form these flotation kind of crust mainly made of anorthite. And so the actual, I would say in broad terms, the minerals and the composition, we find similar things on the Earth. But in detail, if you look at the detailed chemistry, there are differences. And from those differences, that's where the interesting stuff is. That's where you can really sort of piece together what the different histories were of the rock types that formed there.
Have you ever discovered chemicals that have not been found or identified on Earth?
So that's an interesting question in that, the palette of colors, you can think of all the elements as being maybe a palette of colors. It's the same palette for everything that's solid in our solar system and even beyond. I mean, the elements, that make up the different minerals being sort of the ways in which the elements combine. The elements are all the same. There are some different minerals that you find on the moon that you don't find here. So the minerals meaning the combination, the ways in which the elements combine to form sort of solid crystals of different things. some of those types of minerals are different. A lot of the minerals are the same minerals, actually. So, but the different minerals that we find on the moon, they can tell us something about the formation history on the moon. For example, a lot of basalts on the Earth, we can tell that they formed in the presence of a lot more, water perhaps, or oxygen. But on the moon, when they were forming, it was, that was oxygen and water. That's those are components that were not as pervasive or as present, and so they have a somewhat different chemistry. So so I would say that the elements are the same everywhere, throughout all kinds of rock types that we find from other places in the solar system.
That's really interesting, because that makes me think about if there's water on the moon and there's similar chemical composition in the materials that you found there on Earth, but there's life on Earth. I'm wondering about life on the moon. Have you found any evidence of life on the moon, or do you think that we can survive as as a human colony on the moon in the future?
So, there are, from what I understand, at least, and again, there are people that are much more knowledgeable about sort of that aspect about, what it takes to actually get life started.
Oh, sorry, I'm just so ambitious.
No, but but I think it's a great question in the sense that, I think we understand kind of what the conditions need to be to create, to maybe have life be possible. So you have to have the raw materials for some of the key elements that they're called the CHNOPS, carbon, hydrogen, oxygen, phosphorus, sulfur. They're, sort of the backbone of all kinds of, biological compounds and materials. And so some of those ingredients, you need all of those ingredients, but that's not by itself sort of the only condition that's needed. You need some sort of energy source. And so I think, when the moon rocks were first brought back, I think there was, of course, some question about maybe there was potential for life, although a lot of people did not think that there was a high probability of that. But we know at the current time, from having studied moon rocks, that there wasn't life there on the moon anytime in the past. Mars is a different story, of course. I mean, we're going to be bringing back samples from Mars primarily to answer that question: was there ever life on that planet? And there's I think there's quite a likelihood that there are environments on Mars where certainly there might be life.
Martians.
Possible,
so cool.
Right? I mean, microbial life might be still possible, but I think the question for the moon is fairly well settled, except, now with the permanently shadowed regions and the water reservoirs there, again, the idea of having sort of life be able to survive in an environment like that is unlikely. But I think, we'll find out. I think, we're going to be bringing back samples from those regions, but the thought is that, the moon is pretty sterile by and large as far as life goes. And as far as future, maybe there's a way to sort of create habitats there, of course, where humans can survive. But I think, to adapt to the conditions there in a way that you wouldn't need any kind of life support, I think would be kind of, as we know, in terms of how we understand life at the current time, it would be probably very difficult.
Okay, let's talk about meteorites. You became curator of meteorites at Field Museum of Natural History, and then you served as director of the Center for Meteorite Studies at Arizona State University, where you oversaw the curation of one of the largest university-based meteorite collections. What was the most interesting sample in that collection that you came across, and why?
Yeah, that's like asking who's your favorite child.
Well, you won't need to tell me that.
No, but I actually, my really, I guess, favorite meteorites are the Martian meteorites, because that's kind of where I got my start studying meteorites.
Oh, cool. Then tell us about that story.
So my background is in geology. I had minors in physics and chemistry. I loved science as a kid, and just so I came from that sort of terrestrially trained with that backdrop. And when I started grad school, I wanted to study other planets. I didn't quite know exactly how or what exactly I would do at this. And this was early on, of course, in my career. I was just starting grad school. I went to a place, of course, where there were a lot of different people that were studying the solar system and planets from many different perspectives, from spacecraft missions to look at surfaces, doing remote observations, and also studying samples. And I knew that there were meteorites, of course, samples from asteroids, but I had no idea actually that there were actually these meteorites that we thought came from Mars. That was a real revelation to me. I mean, my PhD advisor at the time, she asked me, maybe a month or two after I arrived there, she's like, "Hey, so maybe you wanna look at these rocks that we think are from Mars, and would you want to study that for your thesis?" And I was like, "What? There's rocks that we think are from Mars, and how do we even know that they're from Mars?" And so I actually, the first time I got to see these in a microscope with my terrestrially kind of trained eye for terrestrial geology, Mars meteorites, they look just like run-of-the-mill ordinary basalts that you find here on the Earth. And so I was like, wow, this rock actually formed on another planet, and it still looks so familiar. What an amazing place! I mean, that must have had a really kind of interesting geologic history and a complex history to produce these types of rocks. And so I was just really fascinated early on, just looking at these rocks and just kind of wondering about, and it gave me a way to be a geologist on Mars vicariously. I mean, that's always been kind of my dream, right? To be a geologist and practice geology on another planet. And so I got to do that by studying these Martian meteorites, and that's, they've always been my favorite.
Would you like to go to Mars and study the samples there?
Oh, of course. If I had the opportunity, I would totally go.
Would you take Scott with you?
Yeah, I mean, I think
that would be so amazing.
I would love
Speaking of Scott, I want to ask this. I wanted to ask him, but I ran out of time in season 1. I'm going to ask you this question. So, what is it like being married to an astronaut, such as the legendary Scott Parazynski? And I've been dying to ask this question. Do you guys always talk about space?
Oh, not really. I mean,
you're perfect together. You're just so perfect. I love it.
No, we have actually an uncanny amount of interests that in common, and we think very similarly. It's so strange, because I mean, that was the thing that really struck me when I first met him, was that, wow, I mean, we actually, our thought processes were very similar, I felt, and we grew up in such different cultures and different places, and it's just kind of amazing to me, just how similarly we tend to think about things, and just our sense of kind of wanting to explore and just curiosity and adventure and all of that. I mean, so I mean that's kind of what struck me about him when I first time. It was just like, oh gosh, that's almost like everything.
I love this story.
Yeah. But yeah, I mean, we don't talk about space all the time, of course.
Would you plan to go on a mission together for scientific research?
Oh, I'd love to be able to travel with him. I think it'd be, travel with him to space. I think if that's ever that opportunity ever.
I really hope I see this. I really hope you do. That would be amazing. Okay. So what can we learn about these meteorites, about our past and our future?
Mm-hmm. Well, so we know from studying meteorites actually, and also just studying the history of our planet, is that meteorites have actually shaped the history of our planet over time. 65 or 66 million years ago, the dinosaurs were wiped out along with, 2/3 or actually 3/4 of all life on Earth, because there was a huge impact. And, that's not a one-off. I mean, these things have happened in the past. They will likely happen in the future. It's not a matter of if, it's a matter of when. And we know the probabilities. And so, we know that something like that impact that happened 66 million years ago, the probability is like once every 50 to 100 million years. And, it happened 65 million years ago. It could, so we could have a large sort of body that's maybe, on a collision course with Earth sometime soon, geologically speaking, right? And so we need to be prepared for that. And, we need to understand what these objects really are made of. How do we actually redirect them? We need to understand something about their structure, about their composition, their orbits, all of that, and where they are located in the solar system at the present time. So we need to be studying these objects and understanding them. And meteorites actually, most of them come from asteroidal bodies, and they give us a way, actually, they're sort of a cheaper sample return in a way, in the sense that you don't have to send spacecraft over to all of these objects to bring them back. We've got these space rocks already. And so we can study them to understand sort of how to actually, protect against future impacts by understanding their composition, their structure, all of those types of things. There's also, of course, the possibility that, some of these, sometime in the future, maybe there may be the possibility of using them as resources to supplement the resources that we have here on the Earth. And so, again, understanding the chemistry could have benefits from that perspective. But certainly, I mean, in terms of how we understand so much about our own history up to the current point, everything about our origins, how did this Earth form? How did we end up being where we are? I love
these questions.
Yeah, I mean, they're big human, questions that only human beings can answer. And we're able to do that from studying meteorites. And so it's not really, people tend to think of, studying meteorites as sort of this niche science, but it's not really, because it applies to the very core of, how we got to where we are and understanding our origins. So I think it's a fundamental science.
No, it is. It's fascinating for me. I'm really, really enjoying this. I would love to know if there's any studies on climate change from these samples that you've been studying that you've been able to understand better.
Yeah, so I mean, I think directly, I would say, that's not really something that you would normally look at for meteorites to sort of learn about climate change. But what is interesting is that you can learn something about the history of other planets in our solar system, potentially, like Mars, and the evolution of Mars, for example, and the course that how climate evolved on Mars by potentially looking at these types of rocks. And that can give us potentially some understanding of the kinds of paths that different rocky planets in a system can take. Mars and Earth are actually, both in the so-called habitable zone in our solar system. But why did one planet, evolve in such a different way than the other? And so, it's just sort of the study of meteorites and cosmochemistry, which I'm basically call myself a cosmochemist. try to understand the chemistry of the cosmos and planets and things like that. And
if you were able to understand exactly what chemical composites make up planets, would you make your own little planet? Would you try to make one? Like a mini test? I'm just thinking, I come up with the craziest scientific mad experiments in my head.
No, actually,
I never have the time to do them, so I might as well give you the ideas.
I just actually do that. I mean, they create, we have laboratories in my own school. We have these experimental setups where you can create miniature magma chambers and and
Oh, wow.
create rocks artificially to try to simulate what's happening in nature. So yeah, we absolutely do that. I mean, so there's experimental.
That's so cool.
Yeah. So there's always ways of sort of recreating nature. Of course, the time scales are different. The scale in terms of the spatial scale, temporal scale is very different. But that's the core of sort of a lot of experimental work, is to try to recreate conditions and processes that may happen in nature to get a better understanding of what's really going on. So we do that all the time, yeah.
So there are billions of tiny diamonds and meteorites older than our solar system, known as Stardust, and I got this from your TED Talk as well. Can you please tell me more about this and how they were formed? I mean, diamonds and meteorites, that's blown my mind. That's so interesting.
Yeah, so these are stardust, as I mentioned, pre-solar grains, meaning tiny grains that formed outside of the solar system before the solar system was even formed. And we think that many of these grains actually condensed in the atmospheres of other stars, previous generations of stars before the sun was even born. And so there's actually a study that came out just in the last year that suggests that some of these grains were maybe, 7 billion years old, something like that. So, 2.5, 3 billion years older than our solar system. And so they formed in other places in our galaxy, in stars, in the atmospheres of stars, much before our sun even came about. And so they really are a way to understand what happens in stars, how elements are actually synthesized in the nuclear furnaces of stars. And so they're really kind of fascinating. It's a whole it's a way of doing astrophysics in the laboratory. Instead of sort of looking out with telescopes, we're actually looking in with sort of microscopes and powerful sort of tools to study these tiny grains that can really tell us something about things that are happening way beyond our solar system.
That's so interesting. What is stardust made up of?
So there's many different kinds of stardust, actually. So I mentioned diamonds, of course, and they were the first types of pre-solar stardust materials that were separated from meteorites. But since then, we've found lots of different compositions for pre-solar stardust grains. Some of them are silicate minerals, actually, and they were among the latest ones to be found, because a lot of the rocky materials that make up everything on the Earth and meteorites are basically silicates. So the silica and oxygen combined with other elements. And so, but there are pre-solar grains that have been identified that are silicates as well, but they have a very different, almost, otherworldly, I guess, chemical signatures in them, mainly in what we call isotope signatures for certain things like carbon and oxygen and other elements that we can measure, are so wildly different than anything that we measure in the solar system that's how we know, that they are pre-solar or stardust grain.
So interesting. Do we have any of those chemicals within our bodies?
We have all of those chemicals in our body. I mean, as I mentioned, the palette, of colors or the periodic table of elements as we know it, it's basically the same. And so, in some ways you can think about the fact that, every atom in our body, was actually, it came from either the Big Bang or from subsequent processes that happened in stars. And so, I've said this before, but we are, in a sense, we are stardust, because
that's why I asked.
All of the elements that make up everything that we see around us, including ourselves, it was produced elsewhere at some point in the history of our universe, right? I mean, so either in the Big Bang or in subsequent kind of nuclear processes inside stars.
That's exactly what I thought. But, something happened to me. A few months ago. I noticed like specks of silver, almost like stardust, inside my skin, in my hands. And I mean, that's why I asked the question. I couldn't take it out. I couldn't brush it off either. It was just visible inside the top layer of my skin. I was thinking, oh my gosh, I'm turning into an extraterrestrial.
I mean, but when I say we're made of stardust, I just mean that the elemental components that make up all of our atoms. So I don't mean discrete grains.
I'm going to send you a photograph just so you don't think I'm crazy. I love that. And imagine a jewelry collection made of stardust from another world. That would be amazing and really expensive too.
Yeah.
So you served as a science team member on a number of NASA planetary science missions, including Genesis and Mars Science Laboratory. What was your role in each of those missions, and how did it contribute to the overall success of the mission?
Yeah, so I mean, these mission teams are typically, these are huge endeavors, and lots of scientists, lots of engineers contribute to them. I was, part of the science team for both those missions, and so my own contribution is I would say, I contributed to the science for these by. And my own strength, of course, is in studying the chemistry and the isotope compositions of materials. And so I kind of bring that expertise and perspective. But I would certainly, say that, it's a lot of these missions, the person that's really kind of dominating the science or the direction of these missions, because it is a huge, multi-million-dollar endeavor, which involves, many tens of hundreds of people. And so, so I brought my expertise to the science questions for each of those endeavors.
Amazing. And you went hunting for meteorites in Antarctica. I saw some of your pictures. It's really, really interesting. And that was with ANSMET, which stands for Antarctic Search for Meteorites. Is that correct?
Yep.
What was it like, and what did you discover? And hopefully, I'm wondering whether some of the samples were frozen in ice or not.
Actually, Antarctica is a really fascinating place. It's you do find meteorites on the surface of these ice fields where you collect them. So most of them are actually sitting on top of the ice when you find them. Some of them are actually halfway embedded in the ice, and I'm sure there's many that are actually sort of buried in ice that we never had access to, really. And that's because of the mechanism that actually carries these ice, these meteorites with the ice. That seems to be unique to the Antarctic environment, actually. It's almost like this conveyor belt-like mechanism where these meteorites fall on these ice sheets, and the ice sheets, of course, are moving gradually from the center of the continent out towards the coastlines, and you have these katabatic winds that are ablating the surfaces of ice fields, and particularly in regions where you've got these mountains that kind of the ice comes up against a mountain range, and you have the katabatic winds actually ablating the surface. You can resurface meteorites that had fallen on the ice sheet maybe 10 or 100 million years ago, perhaps as long as that. You resurface them in these kind of zones at the foot of these mountain ranges, or it could even be a subsurface obstruction where the ice is tending to move upwards, and it's being ablated, the surface is being ablated by the wind. So it's just a set of unique conditions that we know occur in Antarctica, and they should actually occur in other places like Greenland, but there have been some expeditions to hunt for meteorites, for example, in Greenland, but there's something different happening there. We haven't really found those same concentrations of meteorites in other places except for the Antarctic.
That's interesting. Why do you think that is?
Yeah, I'm not sure we understand exactly what the difference might be compared to a place in Greenland, for example, where we might theoretically think that you might have similar processes where the ice sheets are moving along and carrying, materials out there. Meteorites, it's not like they're falling any more frequently in Antarctica than any place else. They are falling everywhere on Earth with about the same probability, roughly speaking. So there should be some meteorites that you find in similar kinds of ice fields in other places. that have, we think, similar conditions, but there's something different there. And so in Antarctica, you do find, lots of concentrations of meteorites in these what we call stranding surfaces on ice fields, where you get these concentrations of meteorites. And so, we were able to sort of collect in the last season that I was there. We collected somewhere around 325 or so different, meteorites. And I've been one other time before, and we collected a few hundred meteorites that time as well. And so, it's amazing, though. You understand kind of what's supposed to be going on, and why you find these rocks sitting on the surface. But it's still such a thrill to be able to actually find them when you do.
I would love to go on an expedition with you, just looking for meteorites somewhere in the world. That would be so cool. You were awarded the asteroid name 8356 Wadhwa in 1999 by the International Astronomical Union. How did that happen? And what do the numbers signify, and how did it make you feel?
Yeah, so the privilege of naming asteroids goes to the discoverer, whoever discovers that asteroid they have. So different. Obviously, the history of sort of asteroid discovery has been, it's been sort of more commonly now. There's many more that have been found now, because there's spacecraft that are actually looking for these things as well. But I would say that in the 70s, 80s, 90s, I think it was sort of, telescopic observations, ground-based observations. And I actually, one of my real, heroes in planetary science is Eugene Shoemaker. And his wife, Carolyn Shoemaker, is actually an amazing astronomer as well. And Gene actually had played a very pivotal role, actually, to train the Apollo astronauts. And I think he would have loved to have been the first geologist to go to the moon, and he would have actually, but he unfortunately had a health condition because of which he was disqualified. And so the first man who eventually ended up being the first geologist on the moon, Jack Schmitt. I don't know if you've ever talked to him, but he's a great person. But he was a student of Gene's, and so, I knew Gene and Carolyn, of course, just from, interacting with them in the planetary science community, and they became really good friends. And so Carolyn Shoemaker actually was the one who and Gene and Carolyn discovered the particular asteroid that's named after me. And actually, by the way, Comet Shoemaker-Levy is named after them. I don't know if you remember that comet which hit Jupiter. This happened 1994, I believe.
Oh wow!
So a long time ago, but they discovered that particular comet that with Gene Levy. Actually, it was the other person not Gene Levy. His last name was Levy, of course. But so the Shoemaker-Levy comet is named after them, and so they were prolific. Kind of, they discovered a lot of asteroids, but I was fortunate enough that they chose to name one of their asteroids after me, and this is one that actually goes very close to the orbit of Mars, which is why they named it after me, because they knew that I was, of course, I love studying. That's
really sweet. That's amazing. Yeah. If you could study meteorites anywhere in the universe, where would you go?
Well, I think Earth is a great place to study meteorite. Because, you've got basically an incredible collection of materials that we already have here. And so in terms of, we know that there are meteorites on Mars, for example. We've seen photos from rovers where they've taken these pictures of these iron meteorites there. I would love to study some of those. I think it'd be really cool to do that. There's a certain set of conditions that sort of promotes the survival of some of these objects as they fall through the atmosphere and are decelerated. The moon, for example, just as an example, there's no atmosphere there, of course, and so it doesn't. The objects that are sort of hitting it don't slow down. But then, of course, they don't get ablated in the atmosphere as well. But basically, a lot of them don't survive the impact process. So I would say that I'm actually really thrilled to be able to study the meteorites right here on Earth. I think that
good answer.
So, yeah.
It's good to stay alive and enjoy life while studying meteorites, I guess.
Exactly.
Amazing.
Exactly.
Thank you so much for your time and insight.
Sure.
I could talk to you for hours. Literally, I'm in awe listening to you. But I understand you have to go. This was a great, this was a really great conversation. I've learned so much more about meteorites and their chemical makeup and how you're able to understand the rest of the universe by studying them and the importance of your role. So yeah, thank you for what you do.
Thanks a lot, Sarah. It was great talking to you too.
It's amazing. But I just want to know, where can my viewers or listeners reach you if they wanted to get in touch or follow your journey?
My information is actually on the Arizona State University website. You know, I am also on Twitter and Instagram. So
what's your Twitter?
It's MEENWADHWA, so MINWADHWA.
Okay, perfect. Thank you so much and have an amazing rest of the day, and send my greetings to Scott, and hopefully I see you both up in space.
I hope so. Maybe sometime in the future. I would love that.
I hope so. Maybe Mars. I can see you both on Mars.
Bye, Sarah.
Bye-bye.